Our next paper will be presented by Dr. Lucas. Lucas, I'll give an introduction. Lucas is a naval architect and applied mathematician from TCOMS. He's leading the vessel performance developments in our Center of Excellence for autonomous and remotely operated vessels. And he'll be presenting on deriving of tidal currents from AIS data. Lucas, please.
Good morning, everyone. Thank you, Hian, for the introduction. It's my pleasure to present my paper, my talk today, on the subject of deriving tidal currents using AIS data. But before I begin, just a few acknowledgements. This research, this work, is made possible through the funding support from the National Research Foundation, NRF, and the Singapore Maritime Institute, SMI, through CEOPS, which is the Center of Excellence for autonomous and remotely operated vessels. So CEOPS is hosted at TCOMS. A little bit about CEOPS. CEOPS is the National R&D Center for research associated with maritime autonomous surface ships, or MASS. So some of the work that we do involves developing digital twins of operating environments and modeling vessel performances, ship-to-ship interactions, and also structural health monitoring of vessels. So the agenda for my talk today is as follows. I'll first cover some of the fundamentals concerning ship motions and current interactions. Then I'll present a method used to derive currents from information obtained from AIS data only. It'll be a little bit of a technical talk, but I'll try to keep it relevant to this conference in terms of its applications. Then I will present some of our validation of this method using numerical models, and also real-world AIS data, and then discuss its performance and limitations. So when a vessel moves through current, we can resolve its velocity vectors according to its speed and course over ground, which is basically what we get from GPS data. And its heading, which is basically where the vessel is pointing towards to, and also the speed through water, which is the speed of the vessel in relation to the moving body of water. So AIS data provides only a few of this information: speed over ground, course over ground, and vessel heading. And these come from a combination of GPS and compass readings. So those quantities highlighted in red are what we're interested to solve for. The speed over ground, or speed through water, STW, can be obtained from speed logs or acoustic sensors if a ship has one. And this information, although quite useful, is not submitted or published on AIS. So one way that individual ships monitor surface currents at their present position is to resolve the speed through water and speed over ground to derive the current speed and direction. Now, if the only information from AIS data is made available, we still can derive current speeds and directions. And to do this, we actually have to solve for a system of equations involving the states of two vessels. Of course, we need to assume that both vessels are exposed to the same current conditions. So we went about to put this method into testing using a maneuvering model of a vessel. So this is the framework of the maneuvering model. It's based on mathematical representation of the ship as a system, with inputs to the model being the control actions, your rudder angle, propeller speed, for example, and the outputs of the model being its surge, sway, and yaw motions. The effect of current is modeled by superimposing additional water speeds onto ship speed. Okay, so in this slide, we show some of the results from a test case where we're running the model in 10 knot currents at an 85-degree angle of incidence, as represented by the blue line. Vessel trajectories are plotted for two initial conditions, 10 knot and 15 knot speeds, with 0 and 45-degree headings. So the outputs from the model for these two scenarios, the speed of ground, course of ground, and vessel heading, are used to predict current conditions using the method proposed, plugging it into the equation you see, and then solving for your current conditions. So the predicted current conditions are shown below, and they are more or less equivalent to the input conditions which we prescribed. So this basically demonstrates that the method is valid. This method works, but there are certain conditions to take note of. It's more related to the mathematical limitations, and one of the problem is that this equation becomes badly conditioned in a mathematical sense. When vessel headings from two ships are approximately equal or collinear. Also, another condition is that when current directions are in line with vessel's heading, the problem becomes indeterminate because there's no distinction between the effects of current and changes in ship speed. So we'll revisit some of these conditions in the later slide. And apologies if it's very technical. So just moving on to some real-world data. This proposed method was tested using AIS records from the Western Singapore Straits. Here we show some of the prediction statistics at each 2x2 kilometer grid intervals. So the gray dots denote AIS messages or AIS pings. The black arrows denote the averaged current predictions, and the red arrows are results from tidal prediction models that TCOMS developed. And these are based on hydrodynamic models and astronomical tidal forcing. So we can see that there are some areas where the results have much larger errors, and some of these are due to the sparseness of AIS data in specific areas. These are reflected in the sample sizes on the histogram plots. Other errors are also due to some of the Yiew condition problems which we described previously. So we'll see better examples in the next few slides. Okay, so if we average the results over a period of time, in our case, over a 24-hour window, these are what the results look like for the mean percentage errors of current speeds on the left and the mean absolute errors for current directions on the right in terms of degrees. In this particular scenario, we've applied the following filter conditions you see on the bottom right to improve the accuracy of the predictions. Firstly, we take only AIS pings with speed of ground between 5 and 15 knots. And this really is done to filter out vessels that are anchored, stationary, or moored, and or high-speed craft that tend to have large variations in their speed and course. So that affects some of the predictions. Second condition allows for ships with a steady course. So similar to the first condition, this filters out some of the smaller ships that have rate of turns exceeding 5 degrees per minute. The third condition filters out ill-conditioned variables due to repetition of ship states, and this is enforced by considering the unique MMSI number tagged to each AIS data point. Okay. So in this slide, we have improvements in predictions by applying two more conditions, which basically filter out any collinear course over ground conditions, and also, basically course over ground collinear conditions. So these result in ill condition problems. So with these 5 conditions in place, there are several observations regarding the accuracy. So let's take a look at that. First, we see better predictions away from port. Some examples of that are on the left side of the map in the northwest, southeast, and north to south sea lanes. So the larger errors that are seen closer to port may be due to increased variability in current conditions, due to the influence of land masses and bathymetry changes, for example. So these could result in resolution errors if you're using the 2x2 kilometer grid. We can reduce the grid size. However, there's a trade-off between better resolution and sparseness of the AIS data. And we have, so the third and most observable observation is the large error in the bottom right of the map along the northeast, southwest sea lanes. So the direction in this channel, direction of vessel traffic coincides with current directions. This leads to an condition problem. So just trying to summarize everything. So in this study, we've identified a couple of limitations to this method and proposed some remedies. These are summarized here in the table. And I mean, going forward, there's a couple of areas we'd like to investigate further. One of the areas to improve predictions by accounting for vessel headings of some of these anchored or weather vaning vessels that we see off the coast of Singapore, and mostly in anchorages. So the ships that are anchored will tend to point towards the direction of the oncoming current. If we have this information, this gives us one less variable to solve for that will improve the overall predictions in a larger area. However, a limitation with that is that the location of anchorages around the port of Singapore is quite limited. There are quite a few, but they are at discrete points. And if we couple this with the fact that there's quite large variability in current conditions around port due to influence of land masses, bathymetry, this may limit the use of this method. And I guess another future plan that we had was to expand this investigation to the larger port area. Currently, we're just focusing on the Western Singapore Straits. But if we consider the larger Singapore port, there's more open channels, and this may likely improve the overall prediction. So how does this method actually help in the themes of digitalization and connectivity? I guess by the application of this method would allow for better situational awareness. In the absence of, the speed logs, those information which is not published through AIS, it will give ships a better understanding of current conditions, not just within the vicinity, but over a larger area. So this will help seafarers or in the future, autonomous systems to get a better sense of environmental conditions and then adapt to that, taking the necessary corrective actions. So that brings me to the end of my talk. Thank you for your attention.
Thank you, Lucas. Yep. Any questions from the floor? Yes, Mr. Quet.
Thank you very much. Help me a bit. What's the desired outcome of this particular modeling? First question. Second question, I noticed the wind effect on the ship is not part of the condition. Yeah, that's why is it so?
Yes. So in this case, I guess to answer your first question, the intention with this is to have better mapping of the operating environment, specifically in this case looking at currents, because I think that's most relevant in Singapore waters. And this is done using only AIS data. Of course, there are other ways to get current conditions through numerical modeling, for example, or consulting tide tables. But in the absence of those information, and those information can be limited either due to the lack of computational resources if you're trying to model a port area, or yeah, so in the absence with those limitations, you can use this simple method to get a first cut estimate of current conditions. In relation to your second question on the effects of wind, yes, it has an impact as well, especially if a vessel has a large windage area. That hasn't been accounted for yet. I think that information also comes from onboard sensors, your anemometers and all that. That can be factored into your predictions as well. But yeah, I think one way that we sort of address this is by averaging as well, looking at statistics rather than discrete data points.
Okay. Any further questions? Yep, Siu.
Thank you, Lucas. Can I ask, on the last slide, you mentioned about the inaccuracy of the AIS. So how do you know that which one is the inaccurate data, the sensors or the AIS or the tidal model?
Yeah, so that's one, that's a very important point, the accuracy, and that's variable across ships depending on what kind of sensors they have on board, or how accurate they are, how old they are, whether they've been maintained. I think similar to the previous question on the effect of wind, we try to account for all these errors by looking at statistics, by averaging out the predictions and looking at the mean values, the standard deviation, and then trying to look at the predictions together with its confidence sample size, rather than to just take it as a ground truth.
Thanks, Lucas. Okay, in view of time, we have to move forward, right?